This is a case study on Internet of Things and operational technology cybersecurity. Operational technology includes computer systems and equipment that make changes to the physical world. Sensors, actuators, and computer control systems are critical to safe operation and are increasingly under threat of attack. Industrial sectors include transportation, manufacturing, energy production, power generation, grid networks, and pipelines. A self-driving car has actuators such as steering direction, motor torque, and brake action. Airplane actuators include engine thrust, aileron angle, and flap position. Industrial chemical process actuators include valves and pumps. It is imperative that the command actuator is implemented as requested. There may be a difference between the commanded and actual state of the actuator if there's a cyber attack or equipment malfunction. Cyber attacks may be stealth changes to a process that go undetected but that cause equipment failure, lost economic potential, or health, safety, or environmental incidents. This is a case study with a microcontroller with sensors and actuators. That's the temperature control lab, where the heater, which is the actuator, is monitored to determine if it is on or off. The predicted and commanded heater states are compared to determine if there's an equipment failure or external actor that is taking control of the actuator. A TC Lab digital twin is included with this exercise if the hardware is not connected. Our objective is to first develop a classifier to predict when the TC Lab heater is on and when it is off. We want to generate labeled data where the heater is either on at 100% output or at 0% output for periods between 10 and 25 seconds. So this first data set is a small data set of 10 minutes, and ideally it'd be used for something like testing the methods. The data set can be split into training and test sets, and the data is generated from a TC Lab or sample data is accessed from this link below. There's also a large data set. Now this one, I would encourage you to use it for training. You can also use the simulated TC Lab as well, the digital twin. So the features of the data are selected and scaled between 0 and 1, such as temperature and temperature derivatives. The measured temperature and derivatives and heater value labels are used to create a classifier that predicts when the heater is on or off. The classifier is validated with new data that was not used for training. Let's go down to the exercise. We want to simulate intermittent heater failure by turning down the heater power for periods of about 30 seconds. The heater power is set with lab.p1. The heater power can be set from 0 to 255 and is set to 200 by default. That's an 8-bit representation of the heater power. The simulated cyber attack turns off the heater by setting lab.p1 equals 0 so that no energy is applied even though the heater is requested to a level of 100% with lab.q1 of 100. So there's an example script here that shows how to simulate the cyber attack. We're going to use the classifier to detect when the heater has malfunctioned or is the target of a simulated cyber attack. And in this case, the power is set to 0 or the heater power supply is simply unplugged. So we're going to go through this together. I encourage you to try as much of this as you can. And this is just one possible solution. Let's jump right into the code. I'm going to open up the machine learning course with APMonitor.com/PDS. And then we're going to go down on the right to this applications on IoT and OT cybersecurity. So once that comes up, you'll have this page with the notebook that's right here that you can open up and preview on GitHub. Go ahead and just clone the repository or download that notebook. You can also work this in Jupyter Notebook in Google Colab. So you don't need to install anything on your computer. If you go with the Jupyter Notebook, and that will bring up this same notebook that you can run. Now you won't be able to connect to the TC Lab if you use the Jupyter Notebook that's on Google Colab, because you need to run it locally to be able to connect to this device. So I'm going to go back to just the local version of this and walk through each one. Now a lot of this code is already in there for you. The only thing you need to do is the very last code cell at the very bottom. So these two at the bottom use the classifier to detect when the heater has malfunctioned or is targeted by a simulated cyber attack. So let's just go through the top code as well, and I'll explain it a little bit as I go through each line. So we want to develop this classifier to predict when the TC Lab heater is on and when it's off. And then we'll generate label data where the heater is either on at 100% output or 0% output. Okay, so the very first thing we can do is use a digital twin. And to do that, just type in TC Lab connected equals false. If you change that to true, then the TC Lab is connected and you have the physical hardware there. So I recommend doing this exercise first with this equal to false, and then change it to true if you do have the device, just for one final check, just using the hardware. So what we want to do first of all is just generate some test data with 10 minutes of alternating the heater on and off. So I'm going to import some packages like NumPy, Matplotlib, Pandas, the TC Lab package. You can pip install TC Lab, and time. So I'm going to say if the TC Lab is connected now, then I'm going to connect to it, and else I'll use the digital twin. I'll set this up with connected equals false, and I'll put a speed up in there as well. So I can specify the amount of speed up versus real time, and I'll just say 50 for that, and then I'll connect the lab. And then I have the number of second time points. Okay, so this is going to be 600 for 10 minutes, and I'll create my time points. I'll just initialize, I'll take a measurement, whether it's the simulated lab or the physical one, and do that for T1 and T2. And then I'm going to have my heater values Q1 and Q2. I'll just set those to 0 initially, and then I'll give them some values on when to turn on the heater at selected times. So between cycles 20 to 41 seconds, I'll turn on to 100, 60 to 91, 150 to 81, 181, and so on. So between 0 and 600, I've just selected periods of between 10 to 30 seconds and turned on the heater to 100%. Okay, now what I'm going to do is just set those values. Okay, commanded Q1 and Q2 values, turn those on. Q2 is just equal to 0 right now. And then if the TC Lab is connected, I'll sleep for a second and also print every 10 cycles. So I modulus 10, when that equals 0, then we're going to print this. We're going to print the Q value and the T1 value. Else, we're going to sleep only for 0.02 seconds because we have a 50 times speed up, and then every 50th cycle we'll print that. All right, and then we'll append these temperature values to these lists for T1 and T2, and we'll close the lab. And then we want to save a data file, and we'll just stack the time, the Q values together, and the time and the temperature values. And I'll transpose that after I do a vertical stack. And I'll save that as TC Lab test. And let's just go ahead and run this. Okay, so I'm going to run this first one up here, TC Lab connected, and then I'll run this one. Okay, so you can see it's simulating 10 minutes, 50 seconds at a time. So it's about every second that it produces a new line, but it's simulating 50 seconds of data. And as this is going, we're going to create a plot of the test data. Okay, so we have a figure. I'll make that just a little bit bigger with a 10 by 7. And I'll create a new subplot, turn on the grid. I'll plot time. I'm going to divide by 60 because I want to see minutes versus seconds, and then put in the temperature values with red dots. And I'll assign a label with a raw string so I can put in some LaTeX. All right, and then also the temperature in degrees Celsius. And I'll create another subplot with the Q1 values. So those are my heaters. And I'll save the figure as a PNG file. So here's the simulated data. You can see when the heater turns on, the temperature rises. And when it turns off, the temperature is going to fall. So here is the simulated data for 10 minutes. Now, if you actually had the TC Lab plugged in, it would look similar to this, but every device is a little bit unique. All right, so here's another one. We're going to generate some training data, and this one's going to be a little bit longer. We want to generate heater intervals that last 10 to 26 seconds every 5 to 180 seconds. So I'm going to go through this a little bit faster because we've already been through something very similar. We're just running for a little bit longer. Okay, so all the standard packages, we're going to run for an hour though. Okay, and if it's connected, we'll connect it with tclab.tclab, else we'll use the digital twin. In this case, we're going to speed it up by 100 times instead of 50 times. Okay, same thing, we're creating a new list of T values and Q values. And then we're going to have this random duration. So I'll just use some random number generators in this loop. So if I equals K, okay, equals to 60, then I'm going to generate a new J and K value. So the J is the duration of how long it's on, and K is going to be how long it until the next one happens. Okay, so here I have Q values that are going to be 100 for that duration J. All right, and then I'm going to go through now and run the lab and run these Q values through. If I'm connected, I'm going to connect to the device and print out every 10 seconds. Else, I'll have a speed up of 100 times, so I'm only going to sleep for 100th of a second. And then I'll print out every 250th cycle, so about 2.5 seconds. All right, I'll append those T1 and T2 values and close the lab and save my data file like I did before. So when I run this is going to generate 60 minutes of training data. Every 2.5 seconds, you're going to see just a new value come. Okay, while this is going, let's go ahead and generate our plot. Okay, similar to what we had before. And so this is going to be ready when we finish simulating this. So here's our figure that we've created. And you can see the subplot 1, that's going to be our temperature. And then subplot 2, that's going to be our heater percent. And I'll save it as TC Lab train. So I'm going to generate an hour of data. And this is important because we need to be able to see certain features in our data that tell us when this heater is on and when it's off. And then we can divide it into test and training sets. Just this one, if we want to just use this one, or you can use the 10-minute one. So I generated these two. So if you are using a physical device, you can perhaps run one with a digital twin and then another one with real data. Maybe only take 10 minutes for that. Okay, so this is still, okay, so just finished. We just simulated an hour's worth of data. And here we have our hour's worth of data with the TC Lab turning on or off at random intervals and for random durations as well. And so you can see the average is somewhere around 40 degrees Celsius, but we did have a few times where it turned on a little bit longer. And so you could see it get up to about 65 degrees Celsius. And at the very end, we had that ramp down again. All right, now we want to train a classifier to detect heater function. And we're going to use features such as the temperature and temperature derivatives. One of the things, if you try this just with the feature of temperature or temperature derivative, whether it's going up or down, you're going to miss a lot of the classification, because even when you turn off the heater, the temperature still continues to rise for a period of time. So that isn't a reliable indicator of when the heater is on or off. There's a little bit of a second order lag to it that causes it to have some momentum. And so with that, we want to calculate a second derivative as well as one of our features for this, to be able to monitor the equipment to know when the heater is on or off. Okay, so I'm going to get pandas, numpy, matplotlib. I don't need to import these each time, but each code cell is going to be independent here. So I'm going to import a sklearn preprocessing, this min-max scaler, and then also the train test split. Okay, you can choose to animate the plot or not. I'm going to say no on this, but it'll generate a movie for you as a GIF or GIF or MP4. All right, and loading data, I'm going to load the TC Lab test data or the train data, so file 1 and file 2. And I'm going to choose to just load file 2, the hours worth of data. So let's calculate the temperature and first and second derivatives. What I'm going to do with this is just create a cubic polynomial fit of the temperature using 10 data points. Because if you try to calculate the first or second derivatives, just looking at differences, there can be a lot of noise. And also the temperature control lab has discrete values that it'll go to because it's a 10-bit ADC converter. So there's going to be some discrete level of and also some noise. So I'm going to take 10 values, and I'll take, first of all, my data for DT1 and DT2. I'm just going to have placeholders for my first and second derivatives. And if I'm less than 10, then I'm going to just set the difference between these two. Okay. And I'll do a so what I'm going to do is take I try to limit it, so if I is less than length of data minus 10, so I don't want the last 10 data points. What I'm going to do is take the time and subtract time at the initial point, just so I start with 0. And then I'm going to take my y values. Those are going to be the t1 values. And then create a polynomial fit. This is going to be a third order polynomial that is going to be using these 10 data points. Okay, and I'm going to use that to be able to get the estimate of the derivatives. Okay, I'll evaluate the derivatives at the midpoint at 5 seconds. So this is going to be time equals 5, and the first derivative is just going to be the derivative of a cubic polynomial. So I've taken the derivative, and then this is the second derivative of that. So if you recall from calculus class, if you have a coefficient times t to the third, it just becomes 3 times that coefficient times t to the second. Okay, and this was t squared, and so that 2 comes out front times the coefficient times t. And then this was just the third coefficient times t, and that just equals the coefficient. And then you had another one plus p3, but that one is just going to had no time dependent value in that, so it just becomes 0 for the derivative. And then this is just the derivative of the first derivative to give you the second derivative. All right, else we'll just say that DT1 is not a number, so we won't include that in our training data set. And also for the second derivative, that'll be not a number as well. Now I'll remove the last 10 values because we didn't have this, we couldn't calculate this for the last 10. All right, and then I also have my y values. There's my q. That's my label that I want, which is, is it on or off, 0 or 1? or 100% or 0. Okay, I'll scale my data now. Temperature and second derivative and first derivative 5 seconds. Okay, so here's my min-max scaler. Okay, and I'm going to use the fit transform on this. I'm going to transform x. So here's temperature, first derivative, and second derivative. And I'm going to fit and transform it using a min-max. So I'm going to scale it between 0 and 1 for my feature range. So each of those values between 0 and 1. Then I'll have some output labels as well, where the heater is on or off. And so I'm just going to use true if it's on and false if it's off. And I'll let 50% be the divider for those. Okay, I'll split into train and test subsets, 50% each. So I'll use the train test split function, and this will be my, these are the scaled values that I'm going to now split into an A set. Here's XA and YA, and then a B set with XB and YB. Okay, there's my test size, and I'll have shuffle equals false here. So I want to just test it with one half of the data, or train it with one half of the data, and then test it with the other half. Okay, then plot regression results. You can also have this assess just to look at the train and test values and be able to evaluate them. I'm not going to use this one right now, but it'll show up in orange if they're incorrect, and then blue and red are the true and the false. Okay, so let's do some supervised classification. And if you'd like some help on this with these methods, there's a lot more detail on different supervised learning methods here on the course website. You can go through each one of these and look at the advantages and disadvantages, some sample code on how to use these with an example here on number classification. Let's just go with this one. We're going to use logistic regression. Okay, I'll import a linear model. I'll use the limited memory BFGS update. Okay, so that's a type of solver. And then I'll fit it. Okay, with my A data set, and then I'll predict with my B data set. And that's going to be called YP1. You can assess that if you'd like to generate that plot. I'm just going to comment that out for each one. Okay, naive Bayes. We're going to import that. Okay, this one isn't typically very good, but it's very fast. Okay, we can assess it. The same with stochastic gradient descent. I'm going to import it. I'm going to create my stochastic gradient descent classifier. All right, and then fit it and predict it. All right, k nearest neighbors, 5 nearest neighbors, and I'll fit it and predict. And decision tree as well. So here's a decision tree classifier, max depth 10, random state, and the minimum samples leaf is 5. Okay, I'll fit that and predict. Here's random forest. So each of these have strengths and weaknesses. I'm not going to get into that here. Just setting them up is the purpose of this one. I'll we can go through those website to get a little bit more detail. Okay, let's do support vector classifier. All right, and then neural network as well. Okay, if you get an error or a warning, you might need to increase the number of max iterations. Let's just go ahead and try this. And then we're going to go on to unsupervised classification. So let's say we didn't have the labels of when the heater was on or off. We just wanted to try to generate an unsupervised classification method. K means clustering is one of them. Number of clusters needs to be 2 because you're either on or off. Okay, and sometimes you need to swap these. So sometimes you need to go 1 minus that value just because it doesn't know the difference between on or off. It just says, hey, these are different, and so we're going to try to do some unsupervised classification. All right, here's Gaussian mixture model. It's another good one for unsupervised learning. Okay, I'm going to just swap this one, 1 and 0. And then we have spectral clustering as well. All right, and then let's generate the figure for this. If we're going to animate, we'll use the interactive on to show it, you know, and we'll also make the GIF or GIF file as well. We'll need to import image IO, so you need to pip install that. And there's also, if you want to do a MP4, you also need to install another package. It'll give you an error and give you instructions on how to do that. So here's just some code on how to make that. I'm going to make individual frames and then stitch them together into a movie. Okay, here's my plot. All right, and I'm just going to create a couple of subplots here to show how well the classifier is doing and when it predicts it that it's on or off. Okay, here are all of my classifiers, including the supervised and unsupervised learning. And then I'll have the heater and the time. And if I'm going to animate, now what I'm going to do is just generate these and append them to this list and then create with image IO. So I went really fast through that. You don't need to get into the details of it, but it'll generate the movies for you. All right, I'm going to run this, and it's currently running through all of this code. It's fairly complex. I've given you all of this code, so it'll show you the trained classifiers. We use this for the training data set, and there you can see the temperature. We split it into two, and then we're going to use this for the validation. And you can see the first derivative and the second derivative here. Second derivative is in the black line. The first derivative is in the blue line. And here you can see the performance of the different supervised learning methods, the top 8, and then the unsupervised learning methods, k-means clustering down to spectral clustering. So these didn't do quite as well. This spectral clustering actually probably did the best out of any of them, but still, these are didn't really get the boundary between when it's on or off. So I would recommend, the labeled data and any of these supervised learning methods that are these top 8 here. So you can see when the heater's off, it's predicting at 0 and then on. So I shifted everything down by 1 for each one, just so they wouldn't be on top of each other, but we could see them, the performance of each one as you go down by 1. Okay, the true heater on or off is up here in this with this black line. So now what we want to do is simulate heater failure by turning down the heater power every other cycle. All right, so let's import TC Lab, and I've given you this code already. Here's some speed up if you have a digital twin, and we're going to do a cyber attack. We'll just first of all print out the power level, which is lab.p1. By default, that's equal to 200. And we'll test the cyber attack now. I'm going to print just a line of 40 dashes. The heater power is off. Okay, so I'll set this. This is the cyber attack, simulated cyber attack right here. P1, the power of that heater is 0. So somebody has gone into the system and basically disabled the heater. So even when I request that it's going to be on, okay, at 100%, there's something here that disables that. Okay, P1 equals 0. And then if it's connected, we'll wait 30 seconds, else we'll wait 30 simulated seconds. So we'll sleep for 0.3 because we have 100 speed up. All right, and then we'll print the temperature. All right, just to show if this increased or didn't increase. All right, now the heater power is on, and we'll restore that. It can be between 0 and 255. We'll restore heater 1 power level, and then we're going to print power level. Basically just do a test, wait for a bit, and see if we get a temperature rise. So wait for 30 seconds if it's connected. Else we'll wait the simulated 30 seconds and then print the temperature. All right, so let's go ahead and do this. Here's the heater power is off, and you can see that it didn't change the temperature because the power level is set to 0. And here's the simulation with the heater power on, and you can see it should have risen 7 degrees. So this is just a simple case of, hey, we turned on the heater for a certain period of time, we expect it to increase. But let's generate a classifier to detect when the heater has malfunctioned or is the target of that simulated cyber attack. All right, so I'm going to generate data with simulated cyber attack. Okay, this is going to use the classifiers that we've already trained. If you use the digital twin, I have a speed up of 50 here. And then I have the number of second time points. Okay, so let's just test it for 10 minutes like we did before. I'll create these new T1 and T2 lists. Q1 and Q2 zeros, and then my derivatives as well. So those are going to be my features. And I already have the scaling set for each of those, so I'll need to apply that scaling after I calculate them so that my classifiers will work correctly. So I'll turn on the heater at select times like I've did before. Okay, and then I'll select these 30-second cyber attacks at 70 seconds, 140, and then 400 seconds. So I'll set my P1 values to 200 by default, and then in these 30-second cyber attacks, I'm going to set it to 0, and I'll see if I can detect it. Okay, I'll do that at 140 and then 400. Let's do the detection now. All right, so I have D1, that's going to be my detection, and then I have my classifiers. I'm just going to put those in a list, and I'll just use the supervised learning methods, just the 8 that we had, because the unsupervised learning methods, those didn't work that well. And I'll have my prediction, okay, that is going to be zeros. Okay, so this is going to be the number of rows that I have. That's the number 600 right there by 8. So it's going to be a big matrix of 601 rows, 8 columns, and it'll tell me if I'm predicting that the heater is on or off. Here's my Q1 and Q2 that I've implemented, and I'm going to set my power level from this list that I generated right here. So every cycle it's going to change that from 70 to 100. It's going to be on, but no power to the heater. Okay, temperature control lab is connected. This is the digital twin part of it. With 100 speed up, just sleep for 1/100th of a second and print every 100 time points. I'll append the new temperature value. So this is the only thing that really changes if I use a digital twin or not. All the other commands are going to be the same. So I'll start the detection when above 10 samples, and I'll do the cubic polynomial fit of the temperature using the 10 data points again. I'll get my time values as x and my temperature 1 values as the y. I'll use a polynomial fit with a third order polynomial, and I'll evaluate the derivatives right at the midpoint at 5 seconds. Okay, so there's my time, and there's my first derivative, my second derivative, and then I'm going to put these together into my 3 labels. Okay, T1, DT1, and D2T1, which is my second derivative, and then this is my first derivative here, and then my temperature as well. I'll transform that. So this was my scalar that I had. S1 is my scalar. And instead of fit transform, I don't want to create a new fit for min-max, but I'm going to apply the ones that were there before. I just say take my input x and actually reshape it. Okay, so if you only have one row, you have to do this reshape. Just to fit it into a column vector instead of a row vector. Okay, and then I'll reshape it again, coming out so that it has the appropriate shape for the input. If you don't do this, it'll give you a warning and say, hey, you need to do reshape this way. So it's pretty easy to figure out. Okay, there are my classifier predictions. I have all of my classifiers in this list, CLFS, and you can see those right here. Okay, I have my 8. I'm just going to cycle through each one because I use the same method names. So I'm going to predict based on that XS value that I created right up here. So for each one, I'm going to cycle through these 8. I'll predict, and I'll store it, each one in a successive column in my predict matrix here. All right, and I'll update the detection threshold, and the command is going to be Q1 divided by 100. So that's going to be then scaled to 0 or 1. And then my predict is going to, let's just do the mean value of all of those. Okay, so I'm going to do the mean value of all of the rows, all of the columns in that row. Okay, so I'm going to take an average, and then I'm going to update this detected value with a first order filter. So here's my difference between the two. So if a difference is 1, meaning that I commanded it to be on, but it's actually off, then that's going to be a 1 value. And it's going to take 10% of that and add, so it's going to add 0.1 and then 0.2 and then so it's going to add those up. Actually, I'll multiply it by 0.1 each time for the new one, and then this is going to be multiplied by 0.9 each time. Okay, so that gives you a first order filter, and let's just go ahead and run this. Okay, so it's going to do all of the predictions based on the trained classifiers. Take the average of all of them. Now, some classifiers are going to work better than others, so you may not even want to do an average, but we simulate it for 10 minutes, and then let's generate some plot results similar to what we had before. I'm going to have some height ratios, so I want these first 3 to be a little bit smaller. The last one, I want that to be a little bit more. So I'm going to do a subplot with my temperature. I'll do another subplot with my first derivative and second derivatives, and then I'll do another subplot with the attack. Okay, so plot when the attack was taking place and when it's detected. So this is the most important one right here. This is the attack when something actually happened and how it was detected. All right, and then here's a detection limit, because I say, there's a little bit of error, and so maybe I say it has to get above 0.7 to be able to detect this. All right, and then I'll also build the final one just to show what the classifier average was, which is YP, and then all the individual ones that are going to be in between, calculating that average. All right, I'll save that as detection.png. And so here is the final result right here. Here's our temperature. Here's the temperature first derivative, which is the blue line. And then the temperature second derivative, that is the black line. And you can see when the attack was taking place in the black line here at 70, 140, and then 400 seconds. And then you can see the detection limit, which is the blue dashed line. So if there's a difference for long enough, all of these are predicting 0. It's off, but it's actually on. You're commanding it to be on. Then this is an example of an attack, and you can see that we get above that detection threshold and are able to detect the attack on the system. All right, and you can see that it takes a little bit of time, though. For example, right here, the heater is still off right there for the first 10 seconds. So even though the heater power is 0, I didn't detect that because there's no command to the heater to turn on. So once the heater finally turns on, then you can see this value start to rise. Okay, and you can see that this is the end of the attack right here. So the classifiers start saying, yes, the heater is on. All right, and then similarly over here, it's covered up a little bit, but you can see it through the transparency. It is able to detect this one as well. So overall, we had 3 cyber attacks. We were able to detect each of those as shown here in the plot. Okay, so that's it for this exercise. This is just shows the animation of how those classifiers are trained. But then we use the classifier to detect when the heater has malfunctioned or is a target of a simulated cyber attack. More generally, any piece of equipment that we command to do something and it doesn't do what we commanded, it's either a problem with the signal or a problem with the actual physical equipment somehow. And this method can be used for any type of equipment where you're able to command and then also measure the response, not necessarily even of that thing that you commanded, but things that are related to it. And so we can use these types of classifiers with features that we maybe calculate. Like in this case, we calculated derivatives of the temperature to be able to calculate when the heater's on or off. And similarly with digital twins, we can use those to generate some of these types of training data, especially when we don't have cyber attack data. We may have to use a digital twin to simulate different attack vectors and then be able to train classifiers to detect those. So in this case, digital twins are very helpful in developing these scenarios and being able to learn to recognize them. Hope you've enjoyed this case study. And as I mentioned, the only thing that you really need to do is this final couple cells. I hope you enjoyed it and you learned about how to monitor equipment with potential for cyber attacks.